Hello and welcome to this session. Today we're going to discuss about two important regression models. One is Poisson regression, another is negative binomial. We're going to look into variants of Poisson and binomial, negative binomial, wherein we'll look into offset regression model. We are going to look into zero inflation model. So these are the various variants that we will be looking into as part of this session. Even before we get started with our discussion, I want to quickly expose you to different probability distributions. You know for a fact that we have two types of data. One is continuous, another is discrete. When it comes to continuous distribution, we have normal distribution, we have chi-square, F and T. These four are most commonly used continuous distributions. However, when it comes to not so widely used continuous distributions, we have log normal, exponential, Weibull, and bivariate normal. We are not going to do a deep dive in each of these continuous distributions. However, we're going to discuss about these three discrete probability distributions. We have binomial, we have hypergeometric, and Poisson. These are the three discrete probability distributions which we have. And we're going to discuss about Poisson and negative binomial as part of this session. Let us first expand this and start discussing on what is binomial distribution. Can someone say what does this binomial mean? How many different categories are we going to discuss here? What does binomial mean? Yeah, Monica is right. We are going to discuss two, right? Enoch, that's right, two. Bi means two, right? So we're going to discuss about two categories primarily here. So let me expand binomial. There we go. If we are interested in the occurrence of an event, whether an event is going to occur or not, and not on its magnitude, under such circumstance, we use binomial distribution. What are the two uses of binomial distribution? There are multiple uses, of course. What are two of the primary uses of binomial distribution? One is it will help you determine the probability yield, process yield. Means you can think about yield as productivity, right? It will help you determine the process yield. It will also help you estimate the defective items. So remember one thing, whenever you have binomial, right, or whenever you have defects, we use Poisson regression or Poisson distribution. Whenever we have defectives, we use binomial distribution. Can someone say what is the difference between defects and defectives? What shall I say is the difference between defects and defectives? I repeat, when you are dealing with defects, we go with Poisson regression or Poisson distribution here. Whenever we deal with defectives, we deal with binomial. Okay, Ramanan says defects means how many? That means count. How many defects do we have? Kind of, right? I can have 10 defects, 20, 30 defects, so on and so forth. Defective means category. Is it defective? Yes or no, right? A defective product or a product can have many defects, but still I can use the product. However, if a product is defective, I cannot use that. A defective product cannot be used. Even if I have multiple defects in a product, I can still make use of that. That's the difference, right? Okay. When do we use binomial? As P increases, P means probability. As probability increases, your binomial curve approaches normal distribution. And when does that happen? When your number of data points multiplied by P, and P is greater than or equal to 5, and when your n into 1 minus p is greater than or equal to 5. This is a generic thumb rule. You can remember that, right? This is just a generic thumb rule here. And that is when your binomial distribution approaches normal distribution. And how do we write binomial distribution function? It is once again I've selected this. Okay. I'm sorry, it's not writing, I believe. That's okay. So yeah. And there is one more property of binomial distribution. If your binomial distribution were to approach Poisson distribution, then your n should be large and p should be small. How small should your p be, and how large should your n be? Right, so let me quickly correct this. So your p should be less than 0.1 and your n should be greater than or equal to 16. If these are the values which you have, then your binomial distribution turns out to be Poisson distribution, right? So your binomial distribution can become a normal distribution. Your binomial distribution can also become Poisson distribution, depending on these values of p and n. This is all about your binomial distribution. Then we have hypergeometric distribution. A quick explanation of this, because we'll not be anyway spending a lot of time on this hypergeometric. So I'll quickly run through this. It gives a probability of obtaining elements if those elements are chosen at random without replacement. So if you're going to look into with replacement, then we end up using binomial regression. So let me go to your PowerPoint. Let me go to PowerPoint presentation and quickly explain that, because marker is not writing. Suppose this is a bucket which you have, and suppose all these are the cricket balls which you have. Okay. Now, if I have red and blue balls, for example, if I randomly select one cricket ball from this basket, then there will be a probability associated with that. If I do not replace this cricket ball, which I randomly select from this basket, then for the next experiment, I'm going to have only 5. If I randomly select one cricket ball from this, and if I do not replace that in the third experiment, I would have only 4 cricket balls. So this is called as performing the experiments without replacement. What do you mean by replacement? As part of my first experiment, I select one cricket ball from this basket. For the second experiment, I replace this cricket ball. So for the second experiment also, I'm going to have 6 cricket balls. And for the third experiment also, I'm going to replace the cricket balls, and there will be 6 cricket balls on which I'm going to perform this experiment. Right? And if you are going to replace, and each of the time, if your experimental conditions are going to remain the same, then you go with binomial distribution. If each time your experiment changes, then you go with hypergeometric. Right? So this is an experiment performed without replacement. If it's with replacement, then you end up using binomial distribution. And the third thing is Poisson. If you want to model defects or count data, then you end up using Poisson distribution. If you try to model defectives, then you end up using binomial distribution. This Poisson distribution models number of random occurrences of same phenomena in a unit space or time. And here are few of the examples. For example, arrival rate of customers or cars. That is, number of cars passing a fixed point in a 10-minute interval. Say you have traffic lights, right? And then you're going to monitor how many cars are going to pass that point in 10 minutes interval or 20 minutes or 1 hour. In this way, you can regulate your traffic in much better way, right? In developed countries, you have this concept. You have sensors at each and every traffic signal, and it's going to monitor on what will be the traffic or how many cars or vehicles are going to pass a particular traffic light at a given time. Based on that, the red signal duration, green, right? Those are going to change dynamically, because as and how the time progresses, the number of vehicles passing through a particular route might increase or might decrease. If there is a better route to reach my destination, then I would take that. So obviously the traffic might become less on the other roads, right? Or if you have only one route to reach your office from your home, then no matter what, you are going to take the same route. In that way, right? You can regulate your traffic. So you can use your Poisson distribution in those kind of scenarios. Okay, so this is in brief about binomial and Poisson. Even before we proceed with the regression techniques, I just wanted to expose you to these two basic distributions. Now let me proceed with the advanced regression. So we have already discussed about linear regression. We have discussed about logistic regression. Right, now we are going to proceed to advanced regression techniques. By the way, we have also discussed about multi nomial logistic regression, right? Wherein you have multiple categories basically. Okay, here we go. So the first thing that we are going to discuss today is Poisson regression. Obviously, for you to use Poisson regression, the underlying assumption is that your data is expected to be following Poisson distribution for obvious reasons, right? So Poisson regression is appropriate when the conditional distributions of y are expected to be Poisson distributions. What do you mean by conditional distributions of y? Y given x, right? Condition. What is a y going to be given these x's, given these inputs? That means you're putting some condition, right? Given these inputs, what will be my output basically, right? So this is the first assumption, wherein only if you have your outcome variable which follows Poisson distribution, you end up using Poisson regression. And this often happens when you're trying to regress on count data. Remember, count data. So Poisson regression is used when you have count data, for example, number of insurance claims, number of deaths, so on and so forth. So count data, based on its very nature, would be discrete. And within discrete data, you have count and category basically. So let me quickly try to draw that for you. So if you have discrete data, within discrete data, you can have count data and you can have category. Right? Count is nothing but defects. Category is nothing but defectives. In that sense. When we look at a Poisson distribution, we see a spiked stepped histogram at each value of x. So you'll not have smooth continuous curve like that. You'll have steps. Histogram, right? You'll have those kind of steps basically. And also let me help you show how Poisson distribution looks like, right? By drawing that. Poisson histogram is often skewed. So let me draw that and show it to you. For each value of probability, you will have a different shape for Poisson. If your distribution is like that, then probability would be approximately 0.1. I'm just trying to show you on how Poisson distribution looks like for different values of P probability. If it's like that, then probably this is for probability value of 0.3, and if it's somewhat normal, then it will be probability 0.5. So if your probability is 50% approximately, your Poisson distribution would follow normal distribution kind of, right? And the equation, probability distribution function equation for Poisson regression is P of x is equal to e raised to the power minus lambda, lambda raised to the power x divided by x factorial. And here lambda is equal to mean. All right, the mean of Poisson distribution is nothing but lambda value there. And there is yet another condition for Poisson distribution, which says that mean should be equal to variance. If mean equal to variance, that is when you end up using Poisson regression. Okay, now we know for a fact that it's often skewed towards the right side because of the very nature of the distribution. And if you have small values of y, your outcome variable, right? For small values of y, your Poisson is not symmetric, obviously. Y is nothing but your p value, right? So if p is equal to 0.1, then it's not symmetrical. But for large values, such as p is equal to 0.5, you'll have somewhat symmetric Poisson distribution. So in a Poisson regression, the conditional distribution y changes shape and spread as y changes. That is exactly what I've shown you, right? So at probability 0.1, this is how it's going to look like. At probability is equal to 0.3, this is how it's going to look like. And if probability is equal to 0.5, your curve is going to look a little different, right? So as in how your p-value increases, your Poisson distribution appears to be normal. So Poisson distribution becomes normal shaped and wider as the Poisson parameter increases, as in how your mean increases. So let me write down the equation once again. Probability of x is equal to e raised to the power minus lambda, lambda raised to the power x divided by x factorial. Please spend some time on this equation and let me know what happens if I increase the lambda value. What happens if I increase the lambda value? Please tell me. Probability increases absolutely, Vijay. Right? So e raised to the power lambda, sorry, if the lambda value increases, this e power minus lambda also increases, and anyways you have lambda raised to the power x. If lambda increases, the numerator value is obviously going to increase. If the numerator increases, overall probability value increases. Yeah. As in how your probability value increases, let me show you once again. If p is equal to 0.1, it looks like that. If p value is equal to 0.3, it looks like that. If the p value is 0.5, it looks like that. So as in how your probability value increases, your Poisson distribution becomes normal shape. Yeah. And here is a data set which we have on number of claims. So here are the number of claims, 0, 1, etc. And then here you have the number of vehicles that you have, 1, 2, or 3, and then you have the age. All right, so three things is what you have. Oh, sorry. Here, this is my y, this is my x1, this is x2. We anyways know that y is equal to f of x is the basic equation which we are going to follow. In this case, we have y is equal to 2 inputs. So you're dependent on these two input variables. All right. Now, can I do a simple linear regression on this? Can I do a linear regression on this? Not simple, but can I do a linear regression on this? Oh yes, we can. But what happens if we do that? Let us see what happens, right? Can the number of claims here, it's a linear LMS for linear model, our command, y tilde x1 plus x2, and you have the data in this data set called vehicles, insurance kind of, right? So can I have the number of claims? Can the number of claims be negative? That is my question. No. And here it shows that these values are minimum. Minimum value is negative. Your first quadrant is negative. Medium is also negative. So you cannot have negative values, right? That's one thing. And second thing is that if I use these beta naught, right? So how would the equation be? Number of claims y is equal to beta naught, which is the intercept value here, plus beta 1 x1 plus beta 2 x2. What will be your outcome? Your outcome will be in decimals, right? Your outcome would be in decimals. Can the number of claims be in decimals? Can I have number of claims as 1.6? 1.6 claims. Can I see that? No. It would be either one claim or two claims or three claims or so on and so forth, right? It will not be in decimals. So this somehow linear regression is not fitting in well here, right? So hence we proceed with Poisson. The command to run the Poisson regression would remain the same as GLM, right? Generalized linear model. However, the only change here would be family is equal to Poisson. So y tilde x1 plus x2, and then you say family is equal to Poisson, right? But here, I'll tell you one thing. One way to interpret this is that the outcome value here, which is the number of claims y, is not actually y, it is log of this y. Log of the count. Y is your count. So it's log of count. When you get the value as log of something, then how do I get back the original number? By taking, if I have log of a value, then how do I get back the original number? What do I need to do? Yeah. What do you mean by inverse, Ramanan? We need to take exponential or anti-log, right? And when you do that, you'll get back the number of claims as proper number, 1, 2, 3, so on, so forth. Full number, right? You'll not get in decimal scale. Now, here we're going to discuss about null deviance and residual deviance and also AIC value. Just make a note of this AIC value. Anywhere, right? Anywhere on your book or somewhere, please make a note of this because we're going to refer this at a later point of time. And the AIC value here is 385.51. AIC stands for Archaic Information Criterion. Okay, Archaic Information Criterion. We are going to get back to this in a while from now. So look at this. we have null deviance, which is 287.67, right? Null deviance is obtained if you regress y on your intercept only. If you use only your intercept, which is here, and if you do not use your intercepts for x1 and x2, and if you only use the beta naught, sorry, if you do not use your coefficients of x1 and x2, and if you only use your intercept, that is when you get this value of null deviance. Okay, this is the first way to check your model using only your intercept. The second one is you try to regress your y on intercept, and you're also going to include the two input values, that is your number of vehicles and the age. Once you include your input variables, you get something called as residual deviance. Now apply your logic and let me know on whether residual deviance should be greater than null deviance. Is this situation okay? Just apply your logic and let me know. Ramanan says it's okay. Absolutely right. If you're using, think about these two as your errors basically. So if I'm using only intercept to regress my y, I'm getting a value for null deviance, which is 287, right? The moment I try to include the two input variables, which is x1 and x2, I'm getting slightly less error. I'm getting less error here, 203, right? That means it is a good situation. It's a good case. And if you include your input variables, your error is coming down. That's a good thing, right? So this null deviance and residual deviance is also a way to check your model performance, basically. And then you have your AIC anyways. AIC, I'm going to get back to that. Do not worry at this point of time. You can also do this test, which is called as model fit test. And there's nothing but your chi-square. The only thing that you need to look into here is that if the residual difference here is small, that means if the error is small, the goodness of fit test will not show significant. That means your model fits the data well. And unlike your other scenarios where p-value should be less than 0.05 for the model to be significant, here p-value should be greater than 0.05. Low the residual deviance value, high will be a p-value that's greater than, and it is a good situation. So in this case, we conclude that the model fits reasonably well because the goodness of fit chi-square test does not show statistical significance basically. And if the test had been statistically significant, it would indicate that the data does not fit the model well. The interpretation is slightly different here. Okay, let us move on now further. Here is yet another interpretation. As I've already told you, the regression coefficients are similar to your linear model. However, the only thing is instead of having y, you will get the value log y. And y is nothing but your count variable. Log of count, log count, that is the final outcome that you get. What does each of your regression values say? Let us understand using the outcome variable. Okay, output here. So here you have 0.123273, right? What does this exactly mean? This means that your outcome log y, log count basically, right? Log of number of claims, right? Is going to increase by 0.123 times for every unit increase in your number of vehicles. So if I'm going to increase the number of vehicles by 1, your log count, log of number of claims basically, is going to increase by 0.123 times. Age, let us interpret this also. Log of number of claims would increase by this unit 0.08 for every unit increase in age. If I'm going to increase my age from 30 to 33, it's called as 1 unit change. If the number of vehicles increase from 1 to 2, that's a unit change, right? So for every unit change of your number of vehicles or age, your outcome, which is log of number of claims, would get increased by 0.123 times for your number of vehicles and 0.086 for every unit increase in your age. That is exactly what is mentioned here. Do you have any doubts on that interpretation? And also it's clear from this explanation, this outcome here, that intercept and your age are significant variables because you have 3 stars there, and that is exactly what is mentioned here. The regression coefficient of age is highly significant and the number of vehicles is not significant. Right? The significance of the variables are rather similar to your least squares in linear and Poisson regression. The regression coefficients are not directly comparable since in Poisson regression, the response variable has been transformed into log. So you cannot compare, though they are the same, right? The significance of the variables, both in your linear and Poisson, is the same. However, you cannot compare these two for the only reason that the values or the outcome of your Poisson regression will be transformed into log. So I'll give you just a quick 1 minute time, go through this and ask me if you have any doubts whatsoever. Yeah, I see that someone is unmuted. Yeah, you have a question? Aditya, Enoch, Raman, and Vijay, do you guys have any doubts, any questions on this particular slide? Or let me know if you guys are comfortable with this. Either way.